is a remote presenter, so bear with us for a few minutes while we get that set up.
It's supposed to be unmuted.
Slide one.
Anyone there? Maybe
Where?
here.
Yes, we're here.
I mean,
we can hear you.
sorry.
Yeah,
So,
can you hear us?
Okay,
Kevin.
yeah.
Yeah.
We can hear you.
Okay, great. So we'll get started. I know you guys are running late. There's a little bit of change here. Fortunate to have the president be able to present the first part of this, so I'll let him go ahead.
Okay, y'all ready there? Could I please get some confirmation that you can hear me?
Yeah, Kevin, we can hear you.
Okay. All right. This is Tom Markusik. I'm the CEO and founder of Firefly Aerospace. I'm joined by Kevin Gordon, who is our chief software engineer. And what we're going to do is we're going to talk about our software development experience and approach here, but I wanted to take a few minutes to not only talk about what we've done, but put everything in context of our company and our new space company and what we're doing overall, because I think what we do and how we get there is influenced by that and maybe a bit different than others that are working on larger projects. Okay, slide 2, please. Yeah. All right, so first and foremost, Firefly is a new space company, and I'll wrap up my comments with a few more details on what that means at the end of my intro here. But Firefly in particular is aiming to bring a new space approach to small launch and small to medium spacecraft. And in particular, one of our primary goals is to provide a lower cost, higher frequency access to space for payloads through the way we design things, manufacture and operate these vehicles. A few quick bullet points about the company. We are a U.S. company headquartered near Austin, Texas, so just down the road from y'all. We are led by myself, and I have a lot of background from government, 10 years of government civil service, and I've worked at most of the primary new space companies, SpaceX, Blue Origin, Virgin Galactic, before starting Firefly. We have a lot of senior advisors, including NASA's last administrator, Robert Lightfoot, and former Secretary of the Air Force, Deborah James. Our employees come from all over the industry, and our model is a few really experienced, really veteran, really great leaders surrounded by an army of young, high-energy, brilliant people that we train up to execute. Our first launch vehicle is called Alpha, and it's been designed to ideally address the needs of the small sat market. Next slide. So the technology around Alpha is the simplest, soonest approach. The sizing is sized to dominate the small sat launch market. If you look at a lot of the players out there now in this burgeoning market, it's really a menagerie of people talking about doing small launchers. We studied the problem a lot, and we determined that the ideal payload size was about 1 metric ton, and that's what Alpha is initially designed to. So I would differentiate our launch vehicle from some of the others in that it is actually significantly larger than most of the small launchers that are being fielded out there. It's a very simple 2-stage VoxRP vehicle, uses heritage technology everywhere we can. We want to move fast. We don't want to invent new technology, so we use things that are proven. We buy things off the shelf where we can, and where we can't, we develop things in-house. And it turns out you can't buy a lot of things, so we end up having to engineer and produce and test and flight qualify most of our components. But again, we lean on heritage technology, so it's not too far of a stretch. Okay, next slide. Now, our aspirations at Firefly are not just to build small launchers. I would just, if I could, in a nutshell, I would say that our aspiration is to be the SpaceX of small to medium lift payloads. So if you look at SpaceX, they have really good, robust launch vehicle program, but they also have a really good and robust spacecraft program. And SpaceX, I think part of the success, and I was an early employee there, part of the success was the fact that there was a spacecraft mission beyond the launch mission. So there was a commercial cargo mission that was available that allowed them to get into Dragon development and not only Falcon 9, so spacecraft in the form of Dragon. So I think there are a lot of parallels today. We're fielding our Alpha vehicle, and the most recent opportunity is the NASA Commercial Lunar Payload Services opportunity to develop spacecraft. So there's a lot of parallels there, I think, with commercial cargo that happened in the last decade. So we were fortunate to be selected as one of the providers for commercial lunar payload services. So we're beginning to move out at full speed on our spacecraft development as well while we're doing the launch vehicles. So in space, we'd have the lunar lander, but we also have an orbital transfer vehicle, which is an electric propulsion-based upper stage that can do all kinds of things like plane changes and allow you to do things everywhere in cislunar space. Ultimately, we believe reusability is going to be an important element of any company that wants to be viable long term, and our approach is fundamentally different, I think, than a lot of these vertical takeoff and landing approaches. We believe that we should exploit the atmosphere that's around the Earth and use it for both propulsion and aerodynamic braking. So the vehicle that we ultimately envision as a reusable vehicle is called Gamma, and it's a rocket plane that's illustrated there, kind of the end of the spectrum. Next slide. Here's a view of some of the facilities that we have. We have our engineering headquartered here in Austin. We have a complete metallics capability with CNC mills and a machine shop. We have a complete composite development capability with a large-scale composite facility at our Briggs location, which is about 15 miles from our Austin location. Next slide. Being able to test in-house is a critical part of new space. So we have a 200-acre test facility about 15 miles from our engineering facility where we do rocket engine testing every day. Next slide. And ultimately, launch. Right now, we are in the process of taking over Slick 2 at Vandenberg, which will allow us to hit the polar orbits that we want. Ultimately, we'll have an East Coast launch location as well. Next slide. Okay, so just in conclusion, and to kind of tee things up for Kevin, I just wanted to make one final note about new space and what we're doing and why it's different. So we're trying to go to the same places that people have gone before. We're trying to go to space, but we're trying to get there in a fundamentally different way. And we're not just trying to get there in a different way. No, we're not trying to reinvent the wheel. When we get there, we want to be able to provide lower cost and more convenient service. So, how can you get there? The approach of just going to big aerospace and getting parts and putting them together is not going to work. My experience of going to big aerospace is the first thing they'll say is, "Oh, that's a cute company. That's really nice, son. Does your mom know what you're doing?" Type of thing. And then eventually, if you work on it hard enough, the response that you'll get is, "Okay, fine, we will help you. Could you please leave your wallet and your requirements at the front entrance, and don't call us, we'll call you." Well, that's not going to work. So you end up having to walk away and make this leap of faith and say, "Hey, can we just do this ourselves?" And it's a very hard thing, but ultimately it's been proven that you can do it yourself. And we do this across the enterprise. And this morning, Kevin is going to talk to you about how we do that in particular in software. So allow me to just introduce Kevin. He is one of those people I talked about that's, a preeminent kind of scholar in his field. He has over 30 years of aerospace software development for tactical aircraft, missile systems, satellite systems, and now launch vehicles. So he's leading the effort here. And on that note, I will hand it over to him. If there are any questions at the end for me about Firefly, I'd be glad to circle back and answer those. But I'll hand it over to Kevin now. Thank you.
Thanks. Thank you, Tom. All right. I appreciate that. Tom is in a critical design meeting, was pulled away to give this part of the presentation. So happy that he could do it. Can everyone hear me okay?
We hear you fine.
Oh, okay. All right, so the new space approach that Tom was just describing is the same concept that we took for the software development for the Alpha vehicle. So, you know, really a rare opportunity for me, even with, you know, over 30 years experience on all these aerospace platforms, because it was starting from scratch, which is very atypical. You know, usually you're going into a program that's on block 2 or 3 or something like that with the existing code base. We made the decision there was some code from a previous incarnation, but we decided we were going to take a different path. So that new space approach of simplest, soonest was part of our mantra. And I just have a note here at the beginning, although it's not part of the approach, but just to let you all know, we didn't even start this until January of this year. So I can't stress this enough of sort of going backwards. You know, part of what I'm doing here, besides describing what we did, is to give you all some of our thoughts and ideas of how to do things, I would say, you know, simpler. And that is, you know, don't reinvent the wheel, go COTS whenever you can, but probably the most fundamental thing is to look at all your interfaces that you're going to need to support and make sure that you're going to get a real-time operating system that has those device drivers. Device drivers can be a real situation, I'm sure a lot of you know. So the approach was look at all our interfaces, find an RTOS and a flight computer that all supported that concept. Another sort of driving factor in the approach is we didn't have the luxury of, you know, spending 6 months on defining all requirements, making a design, prototypes, all that. There was avionics hardware in-house that we had to support almost immediately. So a rapid prototyping approach was required. This last bullet here is kind of a lead into some of the lessons learned I'm going to talk about. Probably the biggest point was, you know, make good choices at the beginning so that downstream it becomes much easier and you're not sort of in the weeds and fighting yourself trying to get out of a situation that was produced upstream. Okay, next slide, please. Okay. So with that said, here were some of the decisions that were made in pretty short order, and that was we picked VxWorks, you know, kind of the Cadillac of real-time operating systems, but with some irony, it was actually less expensive than a real-time Linux alternative that we looked at per development seat, and you know, license deployment. So at the same time, we looked at the flight computers, COTS flight computers that would, you know, run VxWorks, of course, and made sure we had all the device drivers off the shelf. The next bullet's really big. You know, my experience with a lot of these real-time systems and, you know, typically already existing code is they're monolithic kernel resident single applications. And those of you that know VxWorks, you don't have to do that, but seems to be the choice. So I decided, let's split this up into different applications and, more importantly, move it out of the kernel space. So VxWorks has the facilities to do that, where each application has its own virtual memory. Pretty important in this way, you're not going to crash the kernel. So another choice, we decided to go C++ for a lot of reasons. I won't get into that, other than to say we believe easier to abstract a solution space in that language. Next bullet here, a lot of people like to assign tasks to specific cores. Wind River has a whole paper on this, and we've kind of followed their advice. We have no core affinity for the 27 task or whatnot that we're going to end up with. We say trust the scheduler. It knows better than we do. Okay, this next to last bullet here about configurability. That was another design choice of, do we hard code stuff as far as devices and whatnot, or do we go fully configurable? For example, if you're going to add another device, you would just change the configuration file and not the source code. So we decided to support that at the beginning. It made developing the code a lot harder, but it's really paid off. I'll describe that in a case that just happened here recently. Last bullet on here, we decided we don't want to put the kernel in the applications actually on the flight computer. We want them on a server so that we can configuration control that, just make it easier to change things. The reason we did that, or an example of why that's beneficial, I'll talk about a little bit later. So next slide, please. All right, this is kind of a busy slide that it says overview the software, but it's actually kind of the whole system. Trying to get across a lot of points here. So the flight software, of course, interfaces with most of the avionics components via network. Not surprising at all. There's a few serial interfaces with things that are typically serial, like IMU, some other devices. So the flight software acquires sensor data, temperatures, pressures, speeds, levels, etc., processes, converts to engineering units, packages, and routes. All the data is needed by internal and external processes. An example of that, GPS and IMU measurements are acquired by the flight software, but provided to the guidance, navigation, and control application. And by the way, that's an example of splitting things up. Kind of shows it over here, GNC controls at the top right. That's a separate application in its own virtual memory space. This, on the right side where it says Rocket Software, a design choice that we've made as far as communication between these separate applications that reside in their own virtual memory space. VxWorks has a beautiful operating system provided way of sharing data with, and they call it a shared data object. So all the data internal that needs to move between these applications are in shared data objects, and it works very well. It's like a pub-sub kind of way of doing things, but a little different viewpoint, because you can actually have multiple publishers, multiple subscribers, and we protect all that, of course, with mutexes. Let's see, commands. Yes, so just talking about what the flight software does, commands valve positions for engines, tanks, thrust vector controls, thrusters, etc. Executes guidance, navigation, control algorithms, and sends control commands to the actuators. Executes commands from the ground. contains a state machine which will execute time sequences for each state and make checks against those. I already mentioned about the configuration. It's extremely configurable via just plain text files. Next slide, please. So I have an example of that. We have, quite a few of these. They are under configuration control, of course, but this is what allows the flight software to, have the flexibility that it does. So at startup, it's reading all these configuration files and, of course, configuring itself for what those configurations are specifying. We do have a separate tool for validating these configuration files so that not only are they syntactically correct, they're semantically correct. So we have these for what you see here is like UDP nodes on the Rocket network. We have these also for serial interfaces, network and serial data definitions. So every piece of data that moves around the system is actually defined in a configuration file. State machine states, time commands and checks, tank pressurization, ground command, definitions, guidance, navigation, control has its own rather large config file. Next slide, please. So just talking about the processes and environments that we're using, like many companies, we're using the Atlassian tool suite of Confluence, Jira, and Bitbucket. Those top two little images here are for those that have seen these tools that will be very familiar. I mentioned, these tools are integrated, so that helps out as far as traceability and visibility. But, one thing we're doing a little bit different, almost everyone is using some agile model, particularly agile-based model, particularly Scrum. We aren't using formal Scrum. We found there's a lot of anti-patterns with, Scrum meetings that everyone has to go to every day. Our Scrums are totally impromptu and sort of naturally organic in the way they occur. And we're also not, Scrum is time-based. We've got Kanban that we use primarily, and if you can see the tiny text, it actually says Kanban board. But we do have sprint boards, but primarily Kanban. What you see on the bottom, so you all already know we're using VxWorks, so of course we're using Workbench, Eclipse-based, with all the Wind River plugins. We're using that to develop, test, analyze. Those of you familiar, you can see the graphic is a system viewer, so that's part of our verification of the operability of the software. So another note, part of verification we conduct through continuous peer reviews, and we also have a nice static analysis tool. Next slide, please. Okay. So how do we do validation? This top one's pretty interesting. At least I hadn't been exposed to it before. The first true application that we integrated, because there was an existing code base, was for guidance, navigation, and control, which was running in a simulation environment. So we took the flight computer and we actually built a PIL, a processor in the loop, specific just for GNC. So we can do, which interestingly enough, we can run faster than real time, which allows for actually Monte Carlos on the actual flight hardware. That's something I'd never seen before, but we wanted to, as quickly as we could, validate that the performance of GNC on the flight computer with that compiler was virtually identical to the simulation environment. So that's really validation for GNC. We have a hardware in the loop lab that duplicates the stages. There's a little shot of it, and we do integration testing with specific avionics hardware, but we can also run scenarios in that Hill lab. It's not 100% mature right now, but it's getting there. And of course, we have validation testing at Briggs for their stage testing. And, you know, we're not going to be TRL-9 until we fly, of course, but doing everything we can. All right, so next slide, please. So I mentioned we started January just absolutely from scratch once we picked VxWorks and the COTS flight computer. So the first thing to do is to, you know, create a bootloader and the kernel build, because, you know, when you have the license, you get the ability to do that. So in short order, in only a couple weeks, we had the bootloader and kernel built. I was just talking about GNC. Other things were going on between January and April, but I just made it a highlight here that we had the validation with the processing in the loop in April. So that actually was on the schedule, but we were able to do that 9 weeks ahead. So these applications to perform different functionality in the flight software, all the prototypes were completed in May, so 6 weeks ahead of schedule. So those applications, those separate you know, RTPs in VxWorks speak, real-time processes, for example, ground to flight software commanding, data acquisition, state machine, tank pressurization, GNC, of course, telemetry, separate application. All those prototypes were working by May. That's only 5 months. That's pretty good for, you know, Tom mentioned the approach here is excellent people and small staff. It was pretty much myself, and I had a helper. So next to the last bullet here, let me see what I'm trying to say. Oh yeah, we started flight software, ground software. So, you know, we had to interface to the ground to perform commanding. That validation was done in July. That was kind of leading to testing at Briggs. So just recently, the flight software was put in the loop out there for stage 2 integration testing, and we're, like, you know, extremely pleased that what you see here in these images is a stage 2 testing and an engine ignition test performed by the flight software. So those integration tests are ongoing, but perform without any failures whatsoever. So very happy about that. Last slide, please. So just some takeaways of what I learned and what we learned with this new space approach and our path forward. You know, it was smart to use COTS and not reinvent the wheel, and a proven basis and focus on the applications. And we made good high-level design choices by getting out of the kernel space and splitting up the flight software into separate components. When I say that's proven to be sound, you know, I'll give you an example. They're trying to figure out something that was going on. I was actually able to remotely connect to the flight computer on the test stand, and while everything else was running, replace one of the software applications with a debug version and debug it real time when they ran a test. So, yeah, that was pretty awesome. Let's see. So the last three are really what we're going to do. You know, of course, we're going to be adding hardware interfaces as those pieces of avionics are added. There's some that aren't there yet. So those will be thoroughly tested in the HITL lab before going out to test at Briggs. supporting integration qualification, that's going on right now, and as everyone has heard, we're of course going to support the launch Q4 next year. See, I do have kind of a main theme here that I'd like to get across. The approach I took, even though I have a lot of experience, I kind of learned how to do things a certain way. So what I wanted to do on this program was really, don't do things just because it's the way it's been done before, how you were taught. Look at, is there a new way to do things? Is there a better way to do things that's, faster, cheaper? And, it's the first time I've ever built the VxWorks application that's in user space and also separating everything, and it's turned out really well. So that's kind of my theme as far as lessons learned. So that's all I have. Tom's in a critical design review. I hate to pull him out, but if there's any questions, I'll try to field them.
Sure, Kevin. So we're opening up to questions right now. Okay. 1 second.
Hi, Kevin. You mentioned briefly your decision to go with C++. Could you comment a little bit on the other alternatives you considered and what factors went into making that decision?
Yeah, sure. In this case, it's kind of my own experience of working with C-only systems for some satellite programs versus some of the other programs I worked on with some of you there where we use C++. It's just, well supported in VxWorks with their compilers, and we just felt like the ability to abstract the problem into solution is just easier. And then, for me, it's a little bit down in the weeds going C only. So that's kind of the basis of the decision, and I think it's worked out well because y'all would be amazed how small this code base is.
Okay, Kevin, can you hear me?
Yes.
Okay, I've got a question from online. The question is the state machine involved in FDIR? And
FDIR. So, yeah, good question. This is a single fault tolerant rocket all around, and also with the software, there's only one compute string. The single fault tolerance is satisfied by AFTU, Autonomous Flight Termination Unit, which will essentially satisfy that by blowing the rocket up. So if there's a fault, whether it's hardware or software induced, for example, you lose IMU, you're pretty much done. So there is no FDIR. It's like, the little engine that could, you just keep trying. And you don't have anything baked into the code that's going to make you exit something based on an error. Okay, and is the basic control loop in GNC PID? There is a GNC team. No disrespect, because I like them, but it's a black box to me. It's an application that has very well-defined inputs and outputs, inputs for sensor data, outputs for controls. I don't know exactly how that's implemented. But it is, the same code base from the sim, all written in C++ as well, and a few tasks. Okay, so we don't have any other questions here. Okay. I think we kind of got through our little issue here, or at least our team here seamlessly got us through it. And so thank you for your presentation. Okay. We appreciate it. All right. Thank you, everyone. Privileged to be able to do this.
Thank you.
All right.